Okay, thanks everyone for coming. My name is Sabi. I'm a student at UT Austin. I'm going to be telling you about how to learn a quantum state with respect to the stabilizer formalism. This is based on a few papers that are all on the archive, and this is joint work with Vishnu Iyer, William Kretschmer, and Daniel Liang. So I want to start off by giving a rough lay of the land when it comes to learning quantum states. Perhaps the most fundamental problem in this area is quantum state tomography. This is where we're given copies of a quantum state rho, and the goal is to output a classical description rho hat of our state that's close to the input state. We've known for over half a decade now that this is a hard problem. So if you have a system of n qubits, you need a number of copies that scales exponentially with n. And a motivating question in quantum state learning is understanding when and how this scaling can be avoided. And the literature that sort of addresses this question breaks into two broad categories. The first thing you can do to avoid the scaling is to just learn less about your state. So instead of recovering the entire density matrix, maybe you have a list of observables and you just want expectation values with respect to those observables. This is like studied in shadow tomography, classical shadows, and pack learning of quantum states. Or you could even try to recover less, like you could try to see if your state has some property. You're just trying to output yes or no. Or you could do even less and just distinguish your state from a Haar random one. The second broad category is using prior knowledge about your system. So a typical thing that's done here is you assume that your state rho is actually coming from a subclass of quantum states. For example, like a matrix product state, a free fermion state, or a stabilizer state. And the thing we care about when we design these algorithms is the number of copies that are consumed by the algorithm, but we also care about the time consumed by these algorithms. And of course, we need the algorithm to be time efficient for us to actually run it on a device. So already on the screen, we see that we don't expect to run tomography on large systems. And these shadow tomography, classical shadows, and pack learning, these have exponential improvements on the copy complexity, but in many cases, these remain exponential time algorithms. And for everything else on the screen, we now have several examples of time-efficient learning algorithms. What we do in this work kind of fits into this picture. We assume that our input state has some structure, and we're able to give learning algorithms in a bunch of different learning models. In particular, we give learning algorithms whose complexity scale with a non-stabilizerness in the input state. And these algorithms are efficient, they're time efficient, when the input state is close enough to a stabilizer state. And what I want to do next is make these statements more precise. I want to explain what I mean by non-stabilizerness, and I want to explain what I mean by close enough to a stabilizer state. In order to do that, I need to review some aspects of the stabilizer formalism. So the first thing to recall is that a Clifford circuit is a quantum circuit comprised of Hadamard phase and C0 gates. This is a really important subclass of quantum circuits. They already exhibit some interesting phenomena like superposition, complex phase, and entanglement. But despite this, we know that they're not universal for quantum computation. And in fact, we can efficiently classically simulate these circuits. This is the Gottesman-Canil theorem. And the other thing to know is that this set of circuits forms a subgroup of the unitary group. And this algebraic structure is one of the main reasons the Clifford group shows up everywhere in quantum information and quantum computation. A mild extension of this gate set is the Clifford plus T gate set. These are unitaries that are comprised of Clifford gates that we just saw. And you can also now use this single qubit gate. This is the T gate. And together, these form a universal gate set. And one should think about the T gate as a limited resource. So in many settings, like error correction, magic state distillation, and near Clifford simulation, the problems are easy when no T gates are involved. And as you introduce T gates into the picture, the problems become dramatically harder. And that's going to be the situation for us as well. The outputs of Clifford circuits are called stabilizer states. So if you take a Clifford circuit and you apply it to the all-zero state, that is a stabilizer state. And one of the key properties of stabilizer states is that they're stabilized by an abelian group of 2 to the n poly operators. And if you don't know, stabilized means that it's a one eigenvector of the operator. And the takeaway here is that you can describe a stabilizer state with a list of generators of an abelian group. And since the order of the group is 2 to the n, we only need n generators. This is a really useful fact. One of the things you can do is you can try to design some algorithms. So like 25 years ago, Gottesman and Knill showed that n-qubit Clifford circuits are classically simulable in polynomial time. And then Aronson and Gottesman and Montanaro showed that n-qubit stabilizer states are learnable in polynomial time. And the natural thing to ask here is, what about Clifford plus T outputs? What about things that are close to stabilizer? And the simulation side of this question has been studied thoroughly for the last 20 years. So we know that if you have circuits with Clifford gates and T gates, you can simulate these in time that scales polynomially with the number of Clifford gates and the number of qubits, but exponentially in the number of T gates. The learning side of this problem has not seen much progress, and one of the main contributions of our work is to complement this simulation result with a learning result. So we show that outputs of Clifford circuits, of Clifford plus T circuits, are learnable in time that scales polynomially with the number of qubits and exponentially with the number of T gates. So if K here, if the number of T gates is order log n, then this is a time-efficient learning algorithm. We also show that outputs of Clifford plus T circuits, where the number of T gates is strictly less than the number of qubits, we show these states are distinguishable from random in polynomial time. And the striking corollary of this result is that pseudorandom states will need at least n T gates to prepare. So this type of distinguishing algorithm implies non-pseudorandomness. I also want to point out that our algorithms are more general than this. They work for any single qubit non-Clifford gate. So the tools we develop work for any single qubit non-Clifford gate. That's going to be true for everything I say, but I'm just going to stick to T-gate to keep things concrete. And we also have a bunch of other learning algorithms that have a similar flavor. Their complexities scale with, like for example, let's look at large stabilizer fidelity implies non-pseudorandomness. This is saying that if your input state overlaps, like has a 1 over poly overlap with a stabilizer state, then that state cannot be pseudorandom. And we have algorithms in a bunch of other learning models as well. They scale with like the overlap the input state has with some stabilizer state or the number of T gates involved in preparing the input state. I don't think it's a good use of time to try to take you through each one of these things or even tell you too much about algorithms. Instead, I want to point you to 2 fantastic hour-long talks that are on YouTube that were given by my co-authors. Instead, I want to focus on some high-level takeaways, some key ingredients that are involved in designing and analyzing these algorithms. And I think this stuff is worth logging in your general knowledge about quantum information. I think it's useful beyond just state learning. And this stuff, some of the stuff I'm going to talk about has already found use in extensions of the NLTS theorem. This was a poster here at QIP. So the first thing I want to say is that non-Clifford operations gracefully remove algebraic structure. So recall that a stabilizer state is stabilized by an abelian group of 2 to the n polys. It turns out that if you have a state that's prepared by Clifford gates and KT gates, then this state also has a non-trivial stabilizer group. In particular, it's stabilized by at least a group that has order at least 2 to the n minus k. And again, this is true for more than just the T gate. The next thing to know is this thing I'm calling the compression lemma. So say you do have a state like this. It is stabilized by an abelian group, G of 2 to the n minus k polys. Then it turns out there is a Clifford circuit that transforms your state to a product state, where the first n minus k qubits are the all-zero state, and the final k qubits are some arbitrary quantum state. And moreover, if you're given the generators of this group G, you can actually search for this circuit, and you can find it efficiently. So high level, what we're doing is we're compressing the non-stabilizerness in our state into just a subsystem of qubits, and we're only using Clifford operations. And because of this lemma, we're actually able to reduce a handful of learning tasks to a matter of learning the generators of the stabilizer group G. The next thing is this p-psi distribution. This shows up like all over the place in our work. So if we take an n-qubit polyoperator W, we can define p-psi on W as the squared expectation of W with respect to the state, normalized by this 2 to the minus n. And it's pretty straightforward to show that p-psi is a distribution over polys. And it's also pretty easy to see that if psi is a stabilizer state, then p-psi has some nice structure. In particular, it's uniform over the polys that stabilize psi. And what we do in our work is we show that p-psi more generally has some nice structure, especially so for a near stabilizer state. This is a little vague, and I don't have too much time to substantiate this claim, but I want to give you some sense of what I'm talking about. So I want to tell you about this thing, the duality theorem. And the duality theorem says that if you have a group G of polys, then the following equality holds for any quantum state. So on the left-hand side, we have the p-psi mass on the group G. And we show that this is always proportional to the p-psi, the probability mass on this object G perp. And G perp is the commutant of G. This is the set of polys that commute with all of G. And so, well, if you prefer the formal definition, here it is. But if you don't, you can ignore that. So this is like a fundamental statement about any quantum state and any group G. We use it a lot in our analysis. And I also want to point out, it might not look like it, but the proof of this theorem just uses Boolean Fourier analysis. So if you're into that sort of math, I'd recommend checking out the proof of this theorem. Okay, the last key ingredient I want to share is the algorithmic primitive that we use in designing our algorithms. It's based on Bell sampling. In Bell sampling, you have 2 copies of your state, and you sort of pair off your qubits and measure them in the Bell basis. So you pair off the first qubits, you measure, you get 2 bits of outcome, and you kind of repeat this. And then your final output will be this length 2n string. And because there's a bijection between f2 to the 2n and n-qubit polys, we interpret this output as a poly operator. So Bell sampling takes in 2 copies of your state, and as output, we get a poly operator. So the algorithmic primitive that we use is called Bell difference sampling. This is introduced by Montanaro in 2017. And then studied further by Gross, Nizami, and Walter in 2021. What you do is you Bell sample twice to obtain 2 strings, x and y, and then you output their difference. And again, this output is a length 2n string, and so we interpret it as an n-qubit poly operator. And Gross, Nizami, and Walter showed a really cool fact that if you Bell difference sample any quantum state, it's drawing a poly operator from easy to write down distribution. It's this distribution q psi, which is the convolution of p psi with itself. In our work, again, we kind of take this further. We show that q psi has some nice structure more generally, especially when it is close to stabilizer. And again, this means prepared with few t-gates or has some large overlap with some stabilizer state. And also q psi has its own duality theorem. And also something that's very useful to know is that if you do have a state psi that is stabilized by a group G of 2 to the n minus k polys, then Bell difference sampling alone suffices to learn the generators of G. Okay, so those are the key things that I wanted to share, but I would be remiss not to at least sketch out one of our learning algorithms at a high level. So I'm going to take you through a high-level sketch of our tomography algorithm. So the input is copies of a quantum state psi that's stabilized by a group G of order 2 to the n minus k. And our output is going to be a classical description of the state. So the first thing we do is we Bell difference sample to learn the generators of the group G. Then we use the compression lemma to efficiently find a Clifford circuit C that maps our state to this product state. And since this final state phi here is like a k-qubit state, and k is like order log n, we can just run quantum state tomography on this state, and this will be time efficient. And then finally, we just output the Clifford C and the description of the k-qubit state, and this is a full description of our state. Okay, so in summary, we have a bunch of new algorithms for learning Clifford plus T states and more. And the algebraic structure of near stabilizer states is very powerful. Okay, yeah, I want to leave with some open problems. The first two are like concrete problems that you could go work on after this talk. They're the hardest problems left in this area, I think, and they're the ones I'm most interested in. The first thing is efficiently estimating stabilizer fidelity. So this is like, the stabilizer fidelity is the maximum overlap your state has with all stabilizer states. We have an algorithm that does this when you're promised that the overlap is at least cosine squared pi over 8. But we do have algorithms that work when we don't have this promise, but they're not polynomial time. The next question is just like tangentially related to what I've talked about. It's, can we distinguish states with stabilizer rank k from random? So if you don't know, stabilizer rank k means that your state can be written as a linear combination of k stabilizer states. And this is a notoriously hard thing to work with. And yeah, I think even making progress on this distinguishing problem would mark some significant progress in our understanding of these systems. The next two things are a bit more vague. I'm not going to say too much about it. Can our techniques improve near Clifford simulation? And are there any interesting connections to draw between our work and stabilizer codes? And there's other stuff that I don't have time to talk about, but I'm here, Daniel and Vishnu, my co-authors are here, and we'd be happy to chat more with anyone that's interested. But yeah, that's all I had. Thanks.
Questions?
Hi, so thank you for your nice talk. So I wonder, does your learning algorithm and like these structural theorems also apply when you want to learn mixed states?
Yeah, that's a great question. No, our techniques only work for pure states. That's a valuable open direction. And generalizing our techniques for mixed states.
Thank you.
Yeah.
Hi, thanks for the great talk. So I wanted to know, how does your result relate to another result by Jens group that they showed that if you have a Clifford circuit and you add one T-gate, then learning the distribution will be hard. And it seems that your result shows that it's easy. So I was wondering how these two relate to each other.
Yeah, so if I recall correctly, that result is, the model is that you have sample access to a distribution, yeah, and you're trying to recover that distribution. Mm-hmm. And here we have like a quantum input. Like we have the entire state, we can apply unitaries and then measure. And so changing that axis model changes the story entirely.
I see. Yeah. But doesn't your model would capture that one as well? In a sense that it seems that yours is more general.
Well, yeah, well, so it's more powerful. Like we have more, yeah, like it's general in the sense that we are able to manipulate the information more, yeah, and extract relevant things efficiently. But if you restricted us to just standard basis measurements, like no, no unitaries before measurement, then that the result you're talking about would say that we have no hope of even recovering the distribution, let alone the state.
I see. I mean, that's interesting. Thank you.
Hi, thanks for the very nice talk. Okay, maybe I don't understand this enough, but can I use your algorithm to estimate the stabilizer rank of a given state?
Yeah, that's, yeah, so the answer is no. I shouldn't have said yeah. The answer is no, but yeah, that is a great question. So Yeah. Like, okay, so the question is, like, we have these different subclasses of quantum states, right? We have the class of states with stabilizer rank K. We have the class of states that overlap, like 1 over Pauli infidelity with stabilizer states. We have states that are prepared with like log NT gates. It's open to relate these classes to each other. We don't know how they relate. I seriously doubt that our algorithm works for stabilizer rank states. And like one thing I'm hoping that comes out of this work is that we have like that we're able to relate this stuff to stabilizer rank, because like that's a really mysterious object that would be great to know more about.
Okay, cool. Thanks.
Yeah.